Whoops. Now that we've solved all of our values. So we end up with 1.8 watts. So yeah, so which one has the smallest current? Resistor 1. So do what? Not necessarily. I'm just saying just as a double check. So in these next steps, so I just was pointing out that this one has the least amount of current, so this should also have the least amount of wattage. So when we do our other calculations, we should still see that trend hold. Okay, so next one. Jessica, you want to solve for the power across resistor 2 or the power across resistor 3? Okay. How much? 5.78 watts. So we have the current of resistor 2 multiplied by the voltage across resistor 2. And we get 5.78 watts, which is what we should expect to see. Because again, the difference between these guys is about 3 times. We should see 3 times as much power being dropped across them. Or, sorry, 3 times less, so you should see the more power because there's more current. So now when we're looking at this one, we need to kind of, make sure our answer is going to make sense. What should we expect to see as far as a value for the power for resistor 3? Ballpark. Slightly less than 5 watts. Okay? Because this resistor is just slightly more, has slightly less current, we should see probably close to 5 watts of power. So if we look at our totals, we have 12.46 watts. We've got essentially 2 there. We've got 5.8 there. So let's see, that's what? 2, 5.8, so that's 6.8. So yeah, we should see about 5.5 watts. Just a rough estimate for values. I like that. Spencer got hit again. Yeah, so that was power for resistor 2. We're on 3. So 141.667 milliamps multiplied by the 34 volts gives us the 4.7 watts. Okay, so just like that, using Ohm's law, voltage multiplied by current will give us power. So 141.667 milliamps times 34 volts, 4.7 watts. Now we want to double check. Do all 3 of these powers add up to equal the 12 and change that we had? They should be pretty close. We right there? Okay. And again, we could have solved for the power for R3 by subtracting the total and subtracting from it the power across R1 and the power from R2. Both of us would have come out and given us the same answer. Or at least, within a couple of milliwatts of each other. So really, with parallel circuits, that's kind of all the heart and soul that they are. The biggest thing is whatever is in parallel with each other is going to have the same voltage drop. So like we said with Max's question, if we had multiple resistors in a branch, that entire branch is going to share or have the combined total of that 34 volts. We'll get into other circuits like, where you might see something that looks like this. Something like that. So whatever's in parallel is going to have the same voltage, and then things that are in series are going to split up that voltage if it's in parallel in systems like that. So just kind of as a heads up, this is what's coming.
So the photoresistance with that kind of thing, you would solve it the same way, or?
You would solve it piece by piece. What's in series? What's in parallel? How do I combine everything together? And then we're going to get into some places where it's kind of hard to determine what's in series, what's in parallel. Like for example, okay, we'll get into a situation where we have this. What's in what? Well, we'll talk about that when we get to that point. But just to show you guys, not trying to scare you, but just trying to prepare you. Huh? Yes. Yes. Because there's also. Because sometimes this is what you're going to do. You want to be able to have this. So there's like we'll go over some of those later, but like there's scales. Use this type of a configuration. The amount of pressure gives you a voltage or a resistance, that kind of stuff. And then what you have to do is you'll actually have a meter in here that'll measure the difference between the two. Your meter has a resistance. So it's the same thing as if we had another resistor in there. And it's going to change based on things. Like I said, we'll go over this, but I'm just showing you that this is some of the things we can. And in this configuration, what's in series, what's in parallel? Not really, there's not an easy way to do that. But I'll show you some other ways to do it. Like I said, I'm not trying to scare you. This is where we're going. Like you guys will be able to solve those circuits when we're done. And that's the idea, is we're showing you these basic steps, these building blocks to where you can get to something like that. And you're like, oh, this is easy. Talk to any of the third and second and fourth semesters. Every single one of them will be like, I wish I could go back to first. It's so easy. And everybody says that about the previous semesters. I mean, heck, I even say about it, once you hit the job field, you're like, adulting sucks. I want to go back to sixth semester. It gets worse as you get, more and more. Once you get established in your career, you're like, oh crap, now I have to pay rent or a mortgage. Now I got to make sure I pay health insurance. I'm responsible for that. Crap, now I have to pay car insurance, college debt. But like I said, that's why we're setting you guys up to be able to get the good jobs to pay for all that, where you don't have to worry about that as much anymore. Okay, anybody have any questions about this circuit? Okay, that's what I like to hear, is I'm getting it. Okay, also, like I said, get on, take the quizzes, take them multiple times, work through them. They should show you the answers when they're done. If they don't, let me know, and I'll make sure there's something checked that'll do it. Because for whatever reason, sometimes they didn't transfer over to where you can see the correct answers. It might take, after you finish the quiz, going back and reviewing the quiz to be able to see it, but it should show you the answers afterwards. And if you don't get an answer, take screenshots of it, text it to me, and we can work it out via that. Or call, or we could even set up a Zoom meeting, and you can go face to face. So, yes? I've been working on getting those fixed. Yeah, so the block 3 should be up and ready to go correctly. I think I have 4 might be done. But yeah, the dates get screwed up. They're supposed to auto update and increment, but Moodle, I think I don't have the right option selected in Moodle for it to do it automatically. So I have to go through and change those. It's true. It was due in 2019 before you even learned about it. Okay. What can we do with parallel circuits? So one thing I've already told you guys that we can actually do with parallel circuits is that's how your houses are wired. Everything needs access to the voltage and not necessarily a specific amount of current. So another way that we can do this is we can build a current meter. So using the exact same meter that you guys have in lab, you can use it to build a current meter for whatever range it is, regardless of what the value says on the screen or what it actually measures. Keyword being there. Even if we just, like I said, with the same meter, we can set it up to do any kind of range. Because think about your DMMs. All you do is change to a different range for current. So in this case, what we're going to have is we have a meter that has 500 microamps to get it to move to full deflection. The resistance of the meter is 1.25 kiloohms. My range, I want to be able to measure 2 milliamps, 25 milliamps, 100 milliamps, and 200 milliamps. So thinking about this, even on this initial range that I have, 2 milliamps is going to do what to that poor meter? If we were to allow 2 milliamps to go through that sucker, it's going to peg that sucker. And it's going to bend the crap out of the internal workings of it. And so it's not going to read or work right ever again. Like you guys are starting to figure out with some of your meters. I'm being serious here. That's why some of those meters read the way they do, is because they're getting slammed on to where they're taking, they're rated for a milliamp, and they're getting pushed 300, 400, 500 milliamps through those things. So then the next time you go to use it, now you have a completely different amount of current that it's going to take to get it in there, because you burnt out part of it, you bent part of it, things like that. Okay, so the first thing we're going to be doing now as we're looking at these guys is we want to determine or I guess for you guys, what do you think is the first step we need to solve for? The voltage of your meter, because that's everything you've been given. We can easily calculate that. So the voltage of the meter is equal to the amount of current we're going to flow through it times the resistance value. So V meter is 500 microamps multiplied by 1.25 kiloohms. Okay, so when this is operating, so the other thing we have to look at is in this circuit, where's our power supply? There is not a power supply, because this thing is going to be another passive meter. It doesn't require any voltage on its own to operate. The voltage and the current it's going to get is coming from what we're measuring. There is no spoon. Okay, so another name for this meter is this is a shunt meter. So what we're having to do is we're wanting to shunt certain amounts of current away from the meter. We want to protect it. So in this situation, we have 2 milliamps. And I'll switch to this color. So we'll go 2 milliamps. Will be in green. So coming up through our probe, we got our plus and our minus on this side. We have 2 milliamps flowing through our circuit. How much current do we want to go up into the meter? 500 microamps. So if we have 500 microamps, how much current do we have that has to go through our shunt resistor? 1.5 milliamps. So now, how can we calculate for what this resistor value needs to be? Okay, voltage divided by resistance. Yeah, voltage divided by current. Yeah, so R1 is equal to the voltage of R1 divided by the current of R1. Do we have all the information we need to solve for this? Yes, why? Because voltage is the same in parallel. When we flow this much current through this resistor, we're going to get that amount of voltage. Yep. So the voltage is going to be the same here. Our current is here. So we have 625 millivolts. We divide that by the 1.5 milliamps. Okay, so we have our maximum range is 2 milliamps. So that's what we want to have flowing through the circuit, and that's what we want this meter to read at 1. So the meter can only take 500 microamps to go full deflection. If we put any more, we're gonna potentially damage our meter. So 2 milliamps are coming in, 500 microamps are going up through the meter. We have to shunt 1.5 milliamps away from there. We have to split it off somehow. Yep. So I shunt to, so IR2 is equal to 2. All right, nope, we're not on 2. Come on, brain. IR1 is equal to the range. So I range minus I meter. Yes?
Why, if let's just make a fix the easiest path available, why would it go on to the next one? That's what it's saying.
So we say it's lazy, it's going to take the path of least resistance, meaning the majority of it's going to take the path of least resistance. So we're still going to get current that goes through here and current that goes through there. We're just going to see more of it coming through the lower resistance.
Oh, that's right. That resistance doesn't
Yeah.
have resistance.
Yeah. One good way to do it. You get a hall packed full, half the hall is packed with big dudes my size. The other side of the hall is packed with people the size of Morgan. People are still going to barrel through either way. It's just going to be easier for them to barrel through the smaller people than it is for the bigger people. But it's still going to move through it. Sorry to pick on you, Morgan, but you're a lot more smaller than I am, so.
So then, like, could you have a resistor that's bigger than the 1.25K, or is that going to really mess up your circuit?
If you have a resistor that's bigger than that, you're going to get more current that goes that direction, which you don't want.
So you have to keep your resistor smaller than the resistor?
Yep.
That makes sense.
Okay. Does that, everybody good with how we got that, for at least for this first step? Yes. You want to go over this one, or do you want to do it with the next step? With the first step. Okay. So we have our range just like we had with the voltmeter. This is the maximum voltage we want, or the maximum current we want to measure in our circuit. Our meter only can go up to 500 microamps. That's the most we want to push through there. But I want to be able to measure 2 milliamps of current total. So what we do is we're going to flow 2 milliamps of current through this device. When we come here, we have to split to protect our meter. So we only want however much current that our meter can handle to go up through that direction. So that gives us 500 microamps going up through the meter. We have to have the rest of it, because of Kirchhoff's current law, we have to have a place for that to go. So from here, it's going to go up, and then it's going to cut this direction. So we're left with the difference between whatever our range is and how much current this guy can take. So that's where we get the 1.5 milliamps from. Then we need to be able to solve for this resistance value. And we do that by looking at what values, or how can I get there? Using Ohm's law, we know that we need the voltage of resistor 1 divided by the current of resistor 1. And the way we can get there is with the voltage, is because R1 is in parallel with the meter. And when things are in parallel, what happens to the voltage? It stays the same. So in parallel, voltage stays the same. In a series circuit, the current stays the same. So in this one, we can figure out the voltage of our meter because we're given both a current and a resistance. So Ohm's law is satisfied at that point. We get the 625 millivolts. That's going to be the same for the voltage across this resistor, this resistor, this resistor, this resistor. Then we can go through and we can take our voltage divided by the current through that branch will give us how much resistance we have to have. So if this value is smaller, it'll allow more current, and we'll see a little bit of a change coming through our meter. Does that help? Okay. So now, let's look at, we go into switch position 2. So this is why I'm writing with different colors, so we can kind of track everything. So now, we've got 25 milliamps coming up. So we have 25 milliamps coming up through here. It's going to hit this point. How much current do we want going up through our meter? 500 microamps. Is it connected in our circuit? If we physically move this switch, yep. So when we move the switch, we are no longer connected to this. This is a what? An open. What's this? An open. What's this one? What's this one? A closed circuit. We have a complete current path. Okay? So yeah, we have 500 microamps going up this direction. How much current do we have coming through here? 24.5 milliamps. Because we have a complete loop. So we could go any direction and we're going to come back to the same spot. Like with this guy, we come up, we can't go anywhere. So it's an open circuit. But this guy has a complete path to get back to it.
So then, if you put the switch to either one, it still won't have closed.
It'll only have a closed loop for whichever one we're connected to. Everything else is going to be open.
So it's like train tracks.
That's all we're doing is, yeah, think of it like train tracks. We're throwing the switch for which route we want to go to. We want to go to Omaha. We want to go to Colorado. We want to go to New York City. We want to go to, Washington, D.C. Why? Very carefully. So, with that, now we need to solve for the value for R2. Again, we take the voltage of R2 divided by the current of R2. This is in parallel with our meter, so this isn't changing. So we end up with 625 millivolts divided by the 24.5 millivolts, milliamps. And the value for R2 not 10, 25. It's all good. So we end up with 25.5 ohms. Gotcha. So, like I said, I struggle a little bit sometimes with dyslexia when it comes to numbers. The way I try to make sure I'm remembering those numbers as I go, and a lot of times when I flip them when I'm just writing here, but when I'm reading the numbers, I learned this trick from an old television show. I don't know if you guys ever saw this or not. I'm probably really, really dating myself. Sequest. Anybody ever heard of it? Okay. So basically what it was an underwater, like the world kind of started to, the ice caps had melted, the place kind of flooded, so most of the earth became water, like more of the earth became water. So everybody was ruling the seas to gain control. They had a great big submarine that was kind of the top of the military line to basically maintain order for them. And what it was is one of the guys on there had dyslexia, and he struggled with it. And what he did to combat it was, when you write out a number or you're trying to transfer numbers, read the number backwards. Because it forces your brain to think about what it's doing instead of just getting into habits, like reading, 416.667. When you go back to double check your numbers or you're trying to transpose it, read it from right to left. So you would start writing 766.614 because it forces your brain to get out of its autopilot and get out of its ruts and think differently. So that also can help, when you're in lab and you're struggling with stuff, read the numbers backwards to make sure you're writing them down correctly. That's also why I put that parallel circuit up backwards, because it makes you stop and think about what am I doing instead of just getting into the ruts and the habits.
I remember my math teachers doing that. They would always write it backwards instead of like this way.
Probably because they're slightly dyslexic when it comes to numbers. Like I said, there's lots of little tricks and things, even from dumb little TV shows. But for me, that stuck out, and I have to do that from time to time because I get myself in a rut, and I keep writing down the wrong numbers, transposing numbers. When I switch to reading it from right to left, it clears things up. It takes me longer, but it clears it up. And if you do things right the first time, it's going to save you time and money instead of having to go back and fix a problem instead of doing it correctly the first time. Accuracy and consistency. That's what we're trying to shoot for. High accuracy, high consistency. Any questions about range 2? Feeling a little more comfortable with it? Okay, let's try range 3. So Simon, I'm going to put you on the spot for a second. Okay? That also, like I said, one of the reasons I pick on people too is when you have to explain something, it sinks in a little bit better in your memory. So don't think I'm trying to pick on you guys. I'm trying to help drive home the points into your memory. Okay, so we're going to try to find range 3. So first of all, what do I need to do? Do what? Okay, we got to find our currents. Okay, so coming up here, we have how much current is going to be flowing. 100 milliamps. We hit this node. How much current is going to be going up to the meter? So when we come up to this point, remember, basically this part's gone, we can just ignore them because they're not connected. So how much current do I want going up this direction? We want the 500. So the 500 we want to come up this direction and go through our meter, but we don't want any more. So we're going to have 500 microamps go up that direction. You'll always have the 500 going that way, or whatever your meter current is, not necessarily this value. Okay? So how much current do we have flowing through R3? Well, we have 500 going this direction. How much is left? Close, minus the 500 micro. So we have 99.5 milliamps. So 500 microamps is 0.5 milliamps. So now we have that, we're going to do the same steps we did. We need to find the resistance value. And so by using Ohm's law, what's our formula? Sorry, I usually try to drive this up. Okay, so if we're looking for resistance, what's our formula? Voltage over current. So we have the voltage across R3 divided by the current going through R3. So in this case, the voltage is going to be whatever voltage we have in here, because that's what we can calculate from. So we have 625 millivolts, and our current, which you said was 99.5 milliamps. What does that come out to be when we divide those out? .281 ohms. Thank you for letting me pick it on you, Simon. So the idea here is we want to figure out how much current is going to be going through this shunt resistor. That's the biggest part of this problem. Because we know how much current is going to go this direction, it's our meter. We just have to figure out how much is coming here. When we have this much current going through here, we know what our voltage is going to be because we have the resistance. Mm-hmm. Yep, exact same steps. Kaylee? These are given to us by our ranges. So in the problem, it said I want 2 milliamps, I want 25 milliamps, 100 milliamps, and 200 milliamp range. Yeah. So in this one, IR2 is equal to I range 2 minus the current meter. IR3 is equal to I range. Okay, and then the last step is we're going to go with our 200 milliamp. So again, we're going to find IR4 is equal to I range 4 minus the current going through our meter. So same steps. So on this one, we will have 200 milliamps going up this direction. We'll have 500 microamps going up to our meter, and that's going to leave us 199.5 milliamps. So then to solve for R4, we take the voltage drop across this resistor, divided by the current of that resistor. So we end up with 625 millivolts divided by the 199.5 milliamps. And that gives us a grand whopping total of how much? 3.13 ohms. It's a 2-branch parallel circuit. That's all it is.
I know, for me, like, I was thinking of, like, we're just doing series, I got you, because it's the one on top of it.
Yep. So next week we're going to get into another type of meter. It's a universal shunt meter. It has a safety feature built into this, because with this guy. So let's talk about this for a second. So now that we have what resistor values we need, what happens if we're in this range at 200 milliamps and we burn up our resistor? What's going to happen? All 200 milliamps is going through that meter. Like it's dangerous for the meter. So this is a shunt meter. Next week we're going to be doing a universal shunt meter, which basically has a built-in protection. So even if the branch was to open, it's still going to limit our current from getting to our meter, which is going to be nice because it's going to keep it from blowing up to just damaging it. And honestly, sometimes it's better to have a damaged part where you know what's happened versus because then it'll still partially work. You still want to replace it, but at least you don't have to replace it before your circuit will work again. Yeah, it's better. Sometimes it's better to have a shoddy fuse that, sketchy, that works sometimes when you're trying to get stuff versus one that just doesn't work. It can be frustrating, but at least you can still limp things through. Okay. So that is, like I said, that is just an application of parallel circuits. So remember, think about your houses and think about, your current meters. So this is what you guys are going to be doing in the lab as well next week. At the end of it, you're going to be building a current meter using the exact same meter board that you guys have. That's why it's really, really important to make sure you find out what the actual current of your meter is. We feel okay-ish with these? Yep. Want to go through all of them again, or do you want to do a new one? A new one with the same style? Okay. Okay, let me grab some numbers. My I meter, 1.7 milliamps. My R meter is 1.007 kiloohms. I want to build a meter that goes, let's see, 200 milliamps, 2 amps, 20 amps, 150 amps. More power. Okay, here's a thought. What would you be using this type of a meter for? Huh? A house. You could build a meter inside your house to be able to show you how much current you're using at any given time. And you could wire this into your circuits. Wouldn't suggest it, but you could. This way you could be constantly monitoring. 150 could be how much current you have total in your house. 20 amps could be a single breaker. This could be a single device, and this could be, also a single device. Phone chargers, they run about 2 amps. 2 amps to 5 amps, depending on the type. Okay, so what we'll do here is let's go ahead and take our break. And then when we come back, we'll take a look at solving the circuit. I'll give you guys some time when we come back as well to start solving it. You did go drop off your fuzzy shirt.
I did.
You got tired of it?
Well, it was so comfortable, I took a nap in it, but then I had to get up.
Yeah, her lab bench is covered in black fuzz.